Hello, everyone. I just wanted to introduce everybody today to the Rack and Power workstream. Today we've got, up to about lunchtime, we've got a selection of presentations that will be addressing the challenges that we're seeing with AI today and how we are addressing them with the latest engineering from a multitude of vendors and customers. So first of all, I'd like to introduce Meta.
Hello, everybody. My name is Glenn Charest. I'm here with Dick Goenner and Tim Marquis, and we're part of the BMQC CLA group, and we're going to give an update on progress our team has made this year. Let's first talk about the makeup of the group. We have expertise across a bunch of areas within liquid cooling. We have manifold suppliers and developers, obviously valve suppliers and developers, rack frame interfaces, and basically ORv3 frame was part of this. The development team was part of this. And we also have hose and tubing solution developers, as well as integrate IT gear developers that helped us develop the IT gear interfaces and concepts. So let me go over the basic design concept for BMQC. It's a holistic solution. It's not just a valve. It's actually a bunch of interfaces and specs that help create a holistic solution. So the frame features an add-on liquid cooling kit that bolts to a standard ORv3 frame, and that was a critical requirement in the development of this effort. We wanted to not have a weldment or a special PID or part number just for liquid cooling, so you can take a standard rack, add this kit to it, and create all the interfaces you need for the manifolds. The manifolds mount to the rear, and that image there on the right, the hot and cold manifolds are split at each rear corner. The IT gear contains the plug connection. The manifolds connect the socket connection of the valves. We'll have some pictures of that in a little bit here. And all the connections are at the rear of the rack. And the valves are designed to self-align during mating between the chassis and the manifolds. Here's a detailed picture here showing the plug mounted to the IT gear in that lower left picture. You can see the plug kind of sitting in that window there, protected in that window area. And then that translucent tube is actually a manifold, and the socket threads into that with an O-ring seal. Let's talk about the valves themselves. Looks like the video is not starting. Oops. You know why that is? Okay. That upper right there's supposed to be a video that worked just fine when we did the dry run. It shows the plug and socket coming together in a line condition and a radial offset condition, as well as combined angle and radial condition. And that lower left picture kind of shows how the plug has a floating body that rotates and adjusts for misalignment and takes up the slop. And so let me kind of go through what the fundamental features of these valve designs are. The socket features an alignment cone that gathers the plug in for alignment. The plug floating body adapts, as I mentioned earlier, for all the misalignment and angle and radial. Also, when it's disconnected and there's no load, it's designed to self-center within its own cup there. It's self-contained. There's no additional components to add float or guidance. And it also has large allowable misalignment as well as a working range. And that's because of all the large tolerances and gaps that are in an IT gear frame interface. I'll talk a little bit about the blind mate manifolds themselves. They utilize standard tubing. However, the key interfaces are machined to precise tolerances. Those interfaces include the manifold alignment features to the frame that also interface to the liquid cooling kit I mentioned earlier, as well as the port interfaces where the socket valves are attached. The design also features design allows for structural rigidity and stiffness because there's quite a bit of forces here from the valves and fluid when you add up all the valve forces in a rack. And then it's an open design. So the connections at the top and bottom for inlet and outlet are open. We really focused on the fundamentals of the interfaces as well as the valve interfaces, rack interfaces, and structural integrity. We didn't really want to focus and be so specific and not give that flexibility to the community. We also did a blind mate IT gear concept. So this is not an actual product. It's actually a proof of concept that we developed that features a novel injector mechanism with compound motion to reduce the installation forces by service personnel when they're putting the chassis into the rack to overcome those forces I mentioned earlier. And the plug valves, again, mount to the rear with a panel nut, and it's installed from the inside out and uses a socket tool that attaches to a common socket wrench. So it's pretty straightforward. And then internal to the design, we have PTFE convoluted tubing that connects from the valves to internal, like cold plates and manifolds. So now I'm going to get over to Nick, who's going to talk about the extensive amount of testing we've done to prove out this design. Thank you.
Yeah, thanks, Glenn. So as the team worked through this project, one key focus area was on making sure that all the different valve designs were interoperable with one another. Because with 4 different suppliers and 2 different mating halves, there are 16 potential combinations of socket and plug that could occur. And the team tested all 16 of those combinations, multiple samples, multiple test sites, both at the fixture level and at the rack level. And the result of all that testing has been a pass. Based on that work, we were able to increase the working pressure to 50 PSI from the original rating of 35. And along with that pressure increase, the team revisited the mate and demate force curves to update those to reflect the increased forces due to the added pressure. We'll get into a few more of those details on the next few slides. So the most basic goal of what we're trying to accomplish here is to deliver flow to the cold plates to provide cooling. So the team took the flow performance of the valves very seriously. And to that end, you can see in our image to the right the flow versus differential pressure curve. And you'll notice that what's a little bit unique about this curve is that the flow is bounded both on the upper and lower side of the nominal curve. And we did this to ensure that the flow performance was very similar with all of the different valve designs, so that when you build up a full rack, the flow remains balanced across all of the chassis. In addition to that, I'd like to call your attention to the image at the lower left side of the screen. You'll see a dimension that we specify as the mate distance, where the valves remain fully open for flow. And if you look at the table, you'll see that there's a 10.5 millimeter stroke range where the valves remain fully open. So not only did we test all 16 combinations, we tested all 16 of them across this entire 10.5 millimeter mate distance range to make sure that the valves always fell within the specification that you see on screen. All that being said, a little bit more variation should be allowed than what you see here because the cold plates are a larger driver of losses in the system. From here, I'd like to highlight a few of the test specifications from the BMQC spec. The first of which is the maximum working pressure, which, as I mentioned earlier, we've raised that to 50 PSI from 35. The spillage has been characterized at both 0 and 50 PSI. And you'll notice that as the working pressure increases, the spillage increases slightly as well. The air inclusion is a measure of how much air gets pushed into the valve during the connect cycle of the valve. And it's limited to 0.1 milliliters per cycle. Our testing confirmed a burst pressure rating both in the coupled and uncoupled states of 150 PSI. And the O-ring blowout test is a stress test where we apply a 55 PSI surge of flow through the valves to ensure that no damage occurs. We tested as high as 10 LPM to confirm our flow rating of 9 LPM. For the temperature testing, we confirmed testing in a environmental chamber. And we've rated the operating temperature at -5 to 60 C with fluid and -40 to 70 C without. The salt spray test is industry standard. It's ASTM B117. The durability test was a mate cycle endurance test. In the wet state, we performed 120 mate cycles, and those were broken up across several different misalignment offsets. Similar story for the dry durability testing. Fewer cycles, these were done at high speed, once again broken up across several different offsets. We specified a maximum mate speed of 0.31 meters per second, but we tested a bit in excess of that to confirm that rating. So with all of this testing at the fixture level, the team wanted to build up some racks and get an understanding of what might happen in the real world. So some of the tests that were performed at the rack level included a shipping and distribution test, and you can see an image of that on the right. We also performed mate cycle testing in the rack with the manifolds installed, measuring forces and confirming the results of the fixture level testing. Safety testing was performed, as well as flow rate and distribution testing. with passing results for all the testing that I've mentioned so far in this presentation. And we'll talk a little bit more about the flow rate and distribution test at a high level on the coming slide. So I've mentioned several times the 16 different combinations of socket and plug that could occur, but in addition to that, there are multiple manifold suppliers and a provision for top versus bottom fluid connection on the manifolds as well. So you can imagine that there's a number of different ways that you can mix and match components to build up a full rack assembly. And the team wanted to understand the impact of that mixing of components with a fully built rack, especially as the flow rates approach the 9 LPM limit. So a full test rack setup was built with 12 chassis installed, and the chassis were instrumented to be able to measure the flow to try to capture the flow variation. And the result of that testing showed that the flow variation was 8 to 9%, which was within the 10% goal. Another finding was that as the number of chassis that are installed into the rack reduced, the flow variation reduced slightly as well. And the final finding was that whether the fluid connection was at the top or the bottom of the manifold, it had very little impact to the flow variation. And from here, I'm going to hand it over to Tim.
Thank you very much, Nick. So learning all of that, I'm sure you're all very excited about how can I know more, what else can I get to? You know, what we have published to the community right now is a pretty thorough actual publication, including the specifications for the BMQC, as well as everything else to be able to to make this system work appropriately. As you can see here, there is a QR code that'll take you directly to this is the BMQC specification. I think you'll find it's very thoroughly laid out all the detailed requirements for all of the valve design and all of the needs you might have in terms of all of the updates and requirements and things to be able to put that into your equipment. In addition to that, it does lay out a pretty detailed set of testing and things to do for other valve manufacturers to become qualified in the future. There is a set of testing, and it does include the interop testing, similar to what the team has done here previously. In addition to that, there is a pretty thorough section on exactly what the test fixturing should look like. This is how we should set it up. This is how the things move together, just to make sure consistency is within all of that testing and make sure that as we go forward, there's not a lot of conflicting results or different interpretations of how to do it. So secondly, on top of that, there goes. There is also, we have contributed the manifold specification. So again, this gives you all the requirements and all the allowances within this design. It gives you the tolerances to be able to get the BMQC within its, you know, it's admittedly very wide tolerance range. It does make up for a lot, but this tells you exactly how to interface it to the rack, what stiffness and material requirements you might have, and be able to include the manifolds within the specification as well. So, on top of that, this team has also updated specification here for the IT gear. Again, it's all the interface requirements, all the stiffness of the sheet metal, all the position tolerances. Glenn and Meta has also included the reference design, and as we've come up with as a team, the new novel injector mechanism that goes in there to be able to hold the gear in as a reference. And then there are some internal hose routing considerations and recommendations. There is some impact in terms of how the hose can be routed and what it does in terms of the actual connection and to be able to keep things consistent. And then to tie it all together, there is an update to the ORv3 frame specification. There's a new section added. It includes all the interfaces. This is how the manifolds mount. This is where you put in the liquid cooling kit. Everything that's included, as well as all the stiffness requirements. And then this really brings the entire set of specifications together so that these can live together as a whole and then be able to give you a complete system as to more than just a set of individual discrete components. So as of right now, you can see there's information out there for all of the manufacturers that participated within this work stream. You can see where to go for all of them. I believe they're all listed now on the OCP marketplace. And there's links to all of the information for each individual one. And I know all the teams have committed to being able to have parts available for samples and to be able to specify this into different systems. So from that, since now you are really excited, you want to get involved. So now there's additional work streams. This is the rack and power work stream where we worked in the cooling loop into the rack and power, as well as there's plenty of things going on within the cooling environments work stream, as well as the cold plate work stream that all of this stuff would tend to apply for. And with that, ask for any questions. Left a few minutes if you have any questions on how this works. Okay. Well, thank you.